Hello students, welcome to EPG Pathsala. I am Professor D. Vel Murugan, former head of the department, Center for Advanced Study in Crystallography and Biophysics from University of Madras, Gindi campus, Chennai, and I am at present working there as the University Grants Commission Basic Scientific Research Faculty. Today, we are going to talk on the module Diffraction by polycrystalline system. We are going to deal with diffraction by a helical chain and also by a discontinuous helix. These are all form a part in the paper Biocrystallography. So students, let us see what we are going to learn in this module. First of all, I am going to introduce you to this concept. Then we are going to learn about the geometrical factors characteristic of the powder method and also about the effects of multiplicity and measured arc length and also practical procedures. We are also in the process going to see the examples of structures determined from powder photograph, how is the diffraction by helical structures, how will be the diffraction by a discontinuous helix. We shall consider the diffraction by a plane of scattering units and by an ideally imperfect crystal. In a crystal, the various planes behave as a diffraction grating, and when a beam of X-rays is incident upon a set of these, the X-rays are scattered according to the conditions of Bragg's law. In the accompanying figure 29.1, we just see how the Bragg's law can be easily elucidated. The amplitude of the wave is scattered by a single plane. Now for example, we are considering two planes PQ and P prime Q prime, and two rays are incident. One is incident on the first plane and another incident on the second plane. If you look at the ray incident on the second plane, it is traveling a larger distance compared to the ray incident on the first plane. So one is now interested in finding the path difference between these two rays scattered from the first plane and the second plane, where the distance between the planes called the interplanar spacing is dHkn. So now AB is the first incident ray and BC is the diffracted ray, which is a scattered ray, and the theta, the Bragg angle or the incident angle, is the angle between the first plane and the incident ray. Now if you drop a perpendicular from the intersection point of the incident ray from the first plane to the second ray at the second plane, so now the left hand side of the perpendicular and the incident ray length will be equal. Similar argument we can extend to the right hand side. If you do this way, the total path difference we can find easily to be equal to 2d sine theta. And for diffraction maximum, the Braggs found that this difference should be the integral multiples of wavelength, or 2d, whenever 2d sine theta equals n lambda, where n is an integer, diffraction maximum can occur. Now, the amplitude of this scattered wave by a single plane can be given as a fraction of the amplitude of the incident wave by the amplitude of the wave scattered from the single plane is given by equation 29.1, where the capital N is the number of diffraction units per unit volume. E, M and C represent the electronic charge, electronic mass and velocity of light respectively. Lambda is the wavelength of X-rays. D is the spacing between the two planes we have considered, and theta is the angle between the incident and diffracted beam with the plane. F is the structure factor amplitude, which depends on the number and arrangement of the electrons in the diffraction unit. When theta equals 0, F has its maximum value corresponding to the sum of the electrons, but as theta increases, F falls off rapidly owing to the interference between the waves scattered by the separate electrons. In powder diffraction, where the crystals are mostly imperfect, the intensity of the diffracted beam is proportional to the square of its amplitude. Taking care of the phase differences between the amplitudes contributed by successive planes, the total quantity of the diffracted beam actually measured is capital Q, which is defined in terms of equation 29.2. This figure 29.2 shows how the atomic scattering factor varies with respect to sin theta by lambda. When sin theta by lambda equal to 0, the atomic scattering factor value has a maximum for each one of these species like hydrogen, carbon and fluorine, and that is nothing but an atomic number. As sin theta by lambda increases or theta increases for a given lambda, it falls exponentially. In the above expression for the capital Q, it was assumed that the incident beam is polarized with the electric vector perpendicular to the plane of incidence. But the incident beam is generally unpolarized, and applying a correction factor of 1 plus cos square 2 theta over 2, the new expression for Q is given by equation 29.3. If the crystal is assumed to rotate with a constant angular velocity omega about the axis which is parallel to the reflection planes and perpendicular to the incident beam, then the total energy capital E, which is diffracted by a crystal as it passes through the angle theta, is proportional to the volume delta V of the crystal irradiated, and the integrated intensity is denoted by the equation 29.4 by E omega over I, which is equal to Q times the delta V, which is equal to n square times e power 4 by m square c power 4 times f square lambda cube over sin 2 theta times 1 plus cos square 2 theta over 2 times delta V. The above equation shows that the intensity of the refracted X-ray beam is influenced by a number of factors. Other factors such as the shape of the specimen, its particle size, its texture, and the geometry of the experimental arrangement also affect the above integrated intensity. The coherence between the diffracted wave trains is reduced due to the thermal motion of the atoms, and as a result, the diffracted beam is weakened. A correction factor e power minus b sin square theta by lambda square has to multiply the atomic scattering factor used in calculating the structure factor amplitude f. In X-ray powder photography, during high or low temperature work, the effect of temperature should be accounted. In some applications, it may be necessary to use different values of the Debye-Weiler factor for atoms of different atomic weights, and the thermal factor will be different depending upon the size of the atom. Now let us consider the geometrical factors characteristic of the powder method. When the sample is in the form of a powder, it comprises of a very large number of crystalline particles. A parallel, non-divergent beam incident upon the specimen will result in the diffracted beams for each plane HKL lying on the surface of coaxial cones with semi-vertical angle 2 theta, theta being the Bragg angle corresponding to each plane. The volume of the powder is so small that the absorption of the incident beam may be neglected, and yet it contains a sufficiently large number of fragments that their orientations may be considered to be completely random. Assuming there are capital M fragments in the powder specimen, I is the intensity of the incident beam and P as the total energy diffracted by the planes, then the ratio P over I equals half times M cos theta times Q delta V. There are fragments of volume delta V. The volume of the powder will be P over I equals half times cos theta Q dot V as given by 29.6. Now let us consider the effects of multiplicity and measured arc length. In a powder photograph, space group symmetry often introduces the possibility of planes with different algebraic combinations of the Miller indices HKL having the same spacing d and therefore diffracting in the same halo. This factor little p is known as the multiplicity factor, and it takes different values for the various crystal classes. Hence, the intensity of diffraction into a given halo is therefore increased by this factor as a multiplier in the above equation. In powder diffraction, where a number of crystallites are there, the intensity of diffraction into the whole halo is not an easy quantity to measure. One is interested in the intensities diffracted into a short length of the halo. If this length is L and capital R is the distance of the point of measurement from the specimen, the ratio of the energy in the length L to that in the whole halo is obviously L over 2 pi r sin theta, and hence the energy diffracted into a short length little l of the halo compared with the intensity of the incident beam is given by P over I, which will be equal to PLQV over 8 pi r sin theta as given by equation 29.7. Let us see the effect of extinction. All the above formulae were derived for mosaic or ideally imperfect crystalline materials, which are composed of discontinuous small blocks of ideal microcrystals. In powder, the particles are generally so minute that no large blocks of ideal crystals are present. But it sometimes happens, particularly if the substance under investigation possesses a marked platy habit, that the blocks have some dimension greater than the mosaic limit. The result of this is that the diffracted beams are weaker than they would be if the blocks were smaller. This effect is known as extinction. If the incident radiation is almost entirely reflected by the upper planes in a block, and the incident radiation which reaches the lower planes is with reduced intensity, it is called primary extinction, which is clearly shown in figure 29.3. Here, the phase changes by reflection at B and C, each by pi by 2, so that between the direction BE and CD, the phase change is pi by 2 plus pi by 2 pi. The process of X-ray reaching the inner planes of crystal is now hindered. Secondary extinction occurs as a result of blocks rather than planes. That is the difference between primary and secondary extinction. If an upper block in a minute crystal diffracts strongly, the radiation incident upon a lower block is reduced in intensity. Lavey provided a quantitative treatment of this effect in 1949 itself. The figure clearly shows what we mean by the secondary extinction. Let us now consider the effect of particle size in this phenomena. The optimum crystal size for X-ray powder diffraction lies between 10 power minus 3 and 10 power minus 5 centimeter. For uniform diffraction halos to be given by a polycrystalline powder, the crystallite size must be within the above limits. It often happens that while making a specimen of crystalline powder, either by rolling or extruding a cylinder or by pressing a block, the particles are caused to align themselves in some preferred way so that the orientation is no longer random. In such cases, a section of the Debye-Scherrer powder diffraction photograph is no longer the true representation of the diffracted beam. Let us now consider the practical procedures. Powder X-ray diffraction can be used to determine the absolute intensities. X-ray powder photography, although qualitative, has been used with great majority and success in quantitative work, both in determination of crystal structure and in the analysis of mixtures. For obtaining the absolute values of the intensities of diffracted beams, the transmission method, method of mixtures, the method of substitution, the ordinary Debye-Scherrer method are used. Many of the earlier structure determinations of metals and alloys were carried out by the transmission method. It is only necessary to measure the absolute intensity of a few planes by this method. Others can be obtained by scaling relative densities obtained by one of the other methods. For sodium chloride, very precise measurements were made. The results on the comparison were found to be in excellent agreement with those obtained from single measurements. In the method of mixtures, the powder is intimately mixed with a known quantity of standard powder whose structure and intensity data are already known. High purity aluminum was used as a suitable standard powder for this method in a series of experiments. Great test of care is necessary in preparing the specimen to ensure homogeneity, randomness of orientation, same particle size, etc. In the method of substitution, the unknown and standard powders are photographed successively either on the same film or preferably on adjacent sections of a wider film in a multiple powder camera. Care is necessary to ensure that the two samples are placed in the same position in the camera and that the X-ray exposure times and film processing times are known for each photograph. The Diffraction method has probably been used for more structure determinations and also for more ordinary X-ray photography than any of the other methods. The specimen is generally in the form of a narrow cylinder. Intensities may be measured by means of microdensitometers. Let us consider some examples of structures determined from powder photograph. It is possible to deduce a structure completely from a powder photograph when a material is simple one and the crystallographic symmetry is fairly high. In general, the powder diffraction method is a powerful one so long as it is at least tetragonal. Lower symmetries result in so many lines of the photograph that the problem becomes far too complex. Most metals and their alloys have had their structures determined by this method, as well as many of the simple minerals and inorganic salts. Amongst the first of the simplest structures to be worked out well, sodium chloride and the other alkaline halides with copper radiation, the X-ray powder photographs comprise about a dozen lines. The structures are cubic with all the atoms lying in special positions in the lattice. Diamond is also cubic, and with molybdenum K alpha radiation, 25 lines were obtained, enabling the correct coordinates for the carbon atoms to be assigned. For arsenic, in Römerhendel structure, 29 lines were obtained on the powder photograph, and the best atomic coordinates were deduced by minimizing the difference between the calculated and observed structure factor amplitudes. In more recent years, as techniques have improved, the complexity of the structure determined has increased. Wide ranges of elements and compounds have been analyzed for their atomic arrangement. For alloys, for example, silver zinc system, 60 lines were observed and their intensities were measured. By a systematic use of offset reflections together with a modified steepest descent procedure for minimizations, the atomic positions were determined with a high degree of accuracy. With modern technology, automated X-ray diffractometers for powder diffraction measurements are all available with built-in sophisticated computer programs for elucidating the three-dimensional structures. One such program is SERPO, released by Professor Giacomo's group from Italy. Let us now consider diffraction by helical structures. A simultaneous rotation and translation along the rotation axis generated a helix with screw symmetry. By screw symmetry, we mean a rotation followed by a translation. A helix along which there are little n equivalent small units of matter per turn is said to have an n-fold screw axis, and n has to be an integer limited to 2, 3, 4 and 6. The theory of diffraction by helical structures was elegantly worked out by groups of Cochrane, Crick and Klug after the proposal of the alpha helix in 1951 by Pauling, the Nobel laureate, and this has been extended and generalized by Lang and Ramachandran. Now let us see how will be the diffraction by continuous helix. A continuous helix of scattering matter can be defined in terms of two fundamental quantities, its radius r and its pitch or rise between turns denoted by capital P. If I denotes 0 or any positive or negative integer, the diffraction pattern will be confined to layers of Z which is equal to I over P. The scattering amplitude expression, analogous to the structure factor expression FHKL, corresponding to single crystal X-ray diffraction, is given by F R comma psi comma I over P equals J subscript L of 2 pi RR e power IL times psi plus pi by 2. J is the Bessel function. And the intensity of diffraction radiation at any point in the pattern is given by I, which is proportional to the above amplitude square, which will be equal to J square of order L of 2 pi RR. Equation 29.9 explains this. The above expression shows that the intensity of the jth layer is hence proportional to the square of the jth order Bessel function and is independent of coordinate or cylindrically symmetrical. The figure 29.5 shows the diffraction pattern of continuous helix. You can see in the right hand side clearly the pattern of X denoted by two cross lines. These Bessel functions of different orders have the appearance of damped oscillations with an important property that the higher the order, the farther from the origin is the first and highest maximum. The diffraction pattern from a continuous helix is therefore a pattern of spots beginning farther and farther from the meridian axis as one goes to higher and higher layer lines, with the strongest and innermost reflections forming the arms of a cross as shown in the above figure. The half angle delta between the meridian and one of the cross is very nearly equal to the pitch angle of the helix. Except for the first few orders, the distance to the first maximum of the jth order Bessel function, J L of x, is very well approximated as xm, which is equal to 2 pi r rm, which is equal to 1.1 times L plus 0.9. The pitch angle beta is defined by the expression tan beta equals P over 2 pi r, and the half angle delta by the expression tan delta equals Rm over Z. It then follows at once that tan delta simply becomes xm over L times tan beta, which is nearly 1.1 times tan beta as given by equation 29.10. A particularly striking example of diffraction by what approximates to a continuous helix is that of wet DNA fibers, which is shown in figure 29.6. So this is simply the diffraction pattern of DNA fiber. Now let us see the diffraction by a discontinuous helix. Consider a negligibly thin helical backbone, again of radius little r and pitch capital P, and place it on a set of atoms or scattering units at equal intervals, h, as measured along the direction of the helical axis. The quantity h is then the rise per scattering unit in the z direction. From these three quantities defined, one can derive other useful ones such as the number of units per turn, little n equal to capital P by h, and the twist per unit or fraction of a turn per unit, little t equal to h over p, which is equal to 1 over small n. It may happen that the helix repeats exactly after distance little z equal to c, in which interval there must be both an integral number of turns capital N and an integral number of units capital M. If so, then it must be true that little c has to be equal to mh, which will be equal to np, and p over h must be a rational fraction. Even when this is not so, Beer has pointed out that it is often convenient to approximate the true helix by one in which p over h is rational and repetition does occur in not too great a distance. One can then index the pattern in terms of odd layer lines, capital Z equal to 1 over c. For a continuous helix, the jth order Bessel function contributes to intensity on the jth layer line. Matters are slightly more complicated for a discontinuous helix, and Cochran, Crick and Van showed that the qth order Bessel function will now contribute to at a height given by Zq equals q over p plus m over h as defined by equation 29.11, or to a layer line I subscript key given by I of q equals nq plus mm, where little m is any positive or negative integer or 0. Meridional reflections with zero order Bessel function will occur at capital Z equal to 0, 1 over h, 2 over h, 3 over h, and so on. And the first one should be at least be a prominent feature of the pattern. Ramachandran in 1960, in a paper outlining the treatment of non-repeating or irrational helices, found it convenient to choose this spacing 1 over h as a fundamental unit of vertical distance, capital Z0, and to measure the displacement above the equator in terms of it, and capital Z equal to eta times Z0, which is equal to eta over n. Now, the qth order Bessel function will appear at heights given by the extremely simple expression eta of q equals tq plus m, or at heights tq, 1 minus tq, 1 plus 2q, 2 minus 2q, 2 plus tq, etc. as given in 29.13. Nothing is now said about the repetitions after n turns or m subunits, or about the diffraction pattern being confined to equally spaced layer lines, and the ratio capital P over n can just as easily be irrational or not. At eta of q height, the contribution of the qth Bessel function is given by equation 29.8 when I is replaced by little q. So capital F as a function of r psi and L over P is given by a product of the Bessel function j order L of 2 pi rr multiplied by e power IL times psi plus pi by 2. If there are many atoms in each scattering unit, then the total scattering amplitude is a sum over the contributions of the individual atoms at various distances from the axis Rj. The exponential factor in equation 29.8 now contains explicit reference to phi j and to zj, angular and the coaxial coordinates respectively of the jth atom. Now we get the 29.13 transformed into 29.14. Diffraction will still occur at the same levels, but the intensity of scattering within a given level will depend on the exact coordinates r, j, phi j and little zj of the individual atoms in the helix. This is entirely analogous to the situation in crystalline solids, where a change in content of a unit cell of fixed size and shape would affect the intensities of diffracted spots but not their positions in the pattern. So, students, let us summarize what we have learned so far in this module. The module explained you in detail the diffraction by polycrystalline materials. The factors affecting the diffraction by crystalline materials is also discussed in this module. The procedures involved in the powder diffraction and methods that are employed to obtain the absolute intensities of the diffracted beam was also explained in the module. The diffraction by continuous and discontinuous helix are discussed in detail. Thank you.